This is the first lecture in our Chapter 14 look at acids and bases. We're going to start with some of the characteristic properties of acids. Acids have a sour taste. You would see this in things like vinegar. Citrus fruits have citric acid, and some other kind of more commonly eaten items. However, when in doubt or when trying to identify a compound or chemical or solution, never use the taste as your defining method of identification. Please don't ever eat any unidentified chemical or any acid that you do not know is food safe. Acids, we have a number of indicators that we use to help us to distinguish or identify between different solutions. You saw an example of this in class. There are kind of three general types of indicator paper. We have blue, red, and orange. Blue indicator paper will turn red in the presence of an acid. Red paper doesn't change at all. And orange indicator paper will also turn red. So red is kind of the color of acids in the lab. Acids will react with most metals or many metals to produce hydrogen gas. Whether or not they will react is based on the activity series, which you probably remember from an earlier chapter. So any metals that are less active can be replaced by the hydrogen in an acid. Acids react with bases to produce water and some kind of inorganic salt. It could have any number of metals as the cation. And all acids conduct an electrical current. So the two groupings of the ways that acids are named we talked about when we first looked at chemical formulas and naming. Remember that acids can be a single element combined with hydrogen, so like HCl, for instance, or HBr. Those are common ones. So in naming a binary acid, we use the term hydro, then the root of the anion, which in this case is chlor, and then the suffix ic. So hydrochloric acid, hydrobromic acid, etc. There are also acids that contain, that contain an oxyanion, so a polyatomic ion that has oxygen and some other nonmetal. And the naming in those cases are based on the anion. So this is sulfate. So when sulfate combines with hydrogen to form an acid, it makes sulfuric acid. Remember that 8 becomes ic. So the 8 part of the anion becomes ic in the acid, and ite becomes us. Here are some examples of common acids and some of their industrial or commercial uses. Sulfuric is H2SO4, and it's used for a whole huge variety of things. I don't expect you to know all of these different uses. I'm just trying to give you kind of an idea of what acids as a group are used for. The next one is nitric, which is HNO3. And actually, this little detail about all of life being nitrogen dependent was intended to go with the nitric acid uses, not the phosphoric acid uses. But nitric acid is used in several kind of exothermic explosive reactions. It's used in dyes and plastics and the manufacturing of all kinds of things. Phosphoric acid is we'll go down here, H3PO4, so it's named for that phosphate, phosphoric. Phosphoric acid is very stable. It's not harmful in many cases, or much less harmful than some of the other acids we'll deal with. It's used in flavorings, cleaning products, things like that. Our next one is hydrochloric, which we've used in lots of examples. And hydrochloric is used a lot of times for removing debris and impurities from metals because it will pull those impurities off and release them as hydrogen gas. It's used in a couple of other functions as well, in addition to being stomach acid. So your stomach digests food using hydrochloric acid. And then our last one is acetic, which is another one we've used quite often as an example. And acetic acid is found in vinegar, lots of food products. It's used to synthesize some chemicals and different kinds of plastic. Okay, the other general compound type that we're going to talk about are bases. Again, bases have a characteristic taste, and that is bitter. Please don't ever taste any unknown solutions or any solutions that are known but their food safety is unknown. Bases also react with different indicators, and the nice thing about bases is bases always go blue. So B and B. Bases will turn red indicator paper to blue. They'll turn orange indicator paper to kind of a blue-green shade. And they won't change blue indicator paper at all because the paper is already blue. Another characteristic of bases is that they feel slippery. This is not something you should use as a characteristic unless you're wearing gloves. Never touch a chemical without more information on what the chemical is. Bases are the other side of this reaction that we talked about with acids. When acids and bases react together, they always produce water and an inorganic salt. And then bases also conduct an electric current. One of the first scientists to really do detailed descriptions on acids and bases and to kind of categorize them in that way was a gentleman named Arrhenius. He was a Swedish chemist. And he kind of identified the fact that when acids are added to water, they increase the concentration of hydrogen ions. That was his defining characteristic of acids themselves. So anything, any solution, any compound that increased the concentration of hydrogen ions, he classified as an acid. So remember, your hydrogen ion is H+. He described bases as anything that increases the concentration of hydroxide. So those are OH-. So when these are added to water, you can see that they cause the water itself to change form in some cases. And the ones that cause a change in hydrogen ions are acids. Those that cause the change in hydroxide ions, the other side of the water, are bases. Just a little bit of a reminder about ionization from chapter 13. Remember that acids on their own are made up of nonmetals, so they are not ionic compounds. But when they are added to water, they ionize. So their component parts separate from one another. And when that happens, so this hydrogen and chlorine are sharing electrons at this point. When that happens, the hydrogen leaves and it doesn't take any of the electrons with it. So it leaves in the form of a hydrogen ion. And that hydrogen ion is very strongly attracted to water because of water's polarity. And so it pretty much instantly forms the hydronium ion. So Arrhenius was correct that hydrogen ions do form, but we know now more information and that the hydrogen ion rapidly becomes actually a hydronium ion. It doesn't stay out there all by itself. We measure the strength of acids and bases by how well they ionize or how many ions they produce total. So strong acids have many ions, weak have relatively few. Most bases have a format similar to this. So they have a metal and a hydroxide ion of some kind, or pardon me, a hydroxide anion. There's one exception, and that is ammonia. Ammonia, when it is added to water, what happens is it busts up this water and it grabs one of the hydrogens away. And so you end up with a positive ammonium cation and a negative hydroxide ion. So that's why ammonia is actually a base, even though it doesn't look like the other bases look. It has a different formula. So the strength and weakness of bases are the same as for acids. Strong bases readily ionize. Weak bases do not readily ionize. And the weak bases are generally those that have low solubility. So they don't dissolve easily, which makes sense because poor dissolving is going to result in fewer ions floating around and therefore a lower ion concentration. So that's it for this set. Please write a summary and bring in 3 questions, and I will see you in class. Thank you.